Students, are you able to hear me? Guys, are you able to hear me?
Sir.
Okay. So I'm just going to the place. I'll log in 2 minutes, okay? So please be online. Don't leave. Yeah, good evening, guys. Am I audible? Yeah. Yes or no? Yes. Okay. So my voice is clear, right? Yes, sir. Okay. So we'll get started with the next chapter, that is thermal properties of matter, right? So till now, we were discussing the mechanical properties, right? So when I say mechanical properties, we were concerned about how will the object respond to the force applied, pressure applied, and all those things, right? Which were trying to change the position of the object. Now, we are going to concentrate on the next topic, that is thermal properties of matter. As the name thermal suggests that there is heat involved, right? So properties, obviously, we are going to see how the characteristics of a matter. When I say matter, I'm talking about solid, liquid, and gas, right? So we will see how will these substances respond to the heat that we apply on the object, right? So in this chapter, we are mainly going to concentrate on solid part. Okay. So before we get started, there are certain basic terms that you need to understand, right? So the first basic term is we need to understand the concept of heat. So what is heat basically? According to us, heat is a form of energy, right? Which produces the sensation of hotness or coldness of an object, right? So when I say the measure of hotness or coldness, I talk about temperature, right? So heat is that form of energy which has something to do with the change in a parameter called as temperature, right? That is why we use the word sensation of hotness or coldness in an object. See, these are all the examples that you already know. See, for example, if there is a piece of ice and we touch, so what is going to happen? Heat is going to flow from where to where? That is an important question. So remember, heat always flows from higher temperature to lower temperature, right? So having said this, what I can say is when you touch ice, heat is actually flowing from our body towards the ice, hence we feel cold. Okay. Similarly, the other example, that is when we stand near a fire, what is going to happen? Obviously, heat from the fire will start flowing towards our body. That is why we feel hot, right? There's something which is known to us, right? The next is there is something called as caloric theory of heat, right? So according to this theory, what we can say is heat is an invisible, weightless, and odorless fluid called caloric. See, this is not much used, but if you know, it is enough, right? So according to this caloric theory of heat, heat is an invisible, weightless, and odorless fluid, which is called as caloric, right? So when some caloric, that is heat, is added to a body, its temperature rises, and when some caloric is removed, that is heat is removed from an object, its temperature is going to fall, right? So this is all about the concept of heat, right? But see, this caloric theory, it failed, right? This theory failed to explain the production of heat by friction. So this was replaced by another theory, which is the dynamic theory of heat. So what does dynamic theory of heat speak about? It says that according to this theory, right, all substances, when I say solids, liquids, and gases, are made up of molecules, obviously. And how are these molecules? These molecules are in a state of continuous random motion, right? So depending on the temperature and nature of the substance, okay? So depending on the temperature and the nature of the substance that you're trying to interact with, the molecules will possess, right, three types of motion. What are they? The first one is they can possess translatory motion, they can possess vibratory motion, right? And they can also have rotational motion, right? So when I talk about translatory motion, what do we say? So translatory refers to an object moving along a straight line. So if a motion is confined to straight line, right, then we have this translatory motion possible, and it is common in gases. And it is common in gases. Similarly, when you talk about the vibratory motion, so vibratory means what? You will have a mean position, and a particle will vibrate about this mean position, producing an amplitude. Amplitude is maximum displacement from its mean position, right? So this kind of a motion is what we call it as vibratory motion. That is, we have a to and fro motion of the molecules about their mean positions, right? Similarly, there is rotation as well possible. So when I have already told, when I speak about rotation, when you talk about a molecule that is revolving about a fixed axis, right? So whenever you talk about the motion of an object around a fixed axis, you call it as rotational motion. So all these points are very important, not only with respect to this chapter, but we will be using these concepts in a topic called as kinetic theory of gases. That is chapter number 13. So at that point, you should understand what are the kinds of motion a gas molecule is going to possess, right? So are you able to understand? Till here, am I clear?
Yes, sir.
Okay. So I'll give you the summary. Don't worry. I'm just giving you the whole story of how the introduction of this chapter is going to be. Next is, obviously, when an object is heated, what will happen to the molecule speed? They are going to increase. They are going to become fast, right? So kinetic, then when the molecules are going to be fast, obviously kinetic energy is involved with them. So kinetic energy due to each type of motion will increase. When I say each type of motion, it is due to the translatory, vibratory, and the rotational motion. All are going to increase. So we can regard heat as an energy of molecular motion, which is equal to whom? The sum of the total kinetic energy possessed by the molecules of a body, by virtue of whom? By virtue of their translational, vibrational, and rotational motion. So if I have to write the mathematical formula, we can write that the energy possessed by the molecule is going to be equal to the sum of the translational kinetic energy, vibrational kinetic energy, plus the rotational kinetic energy. So this can be called as the mathematical expression for the energy possessed by a molecule's motion. I hope it is clear, no?
Yes, sir.
Okay, next. What are the units of heat that are possible? So when I talk about the units of heat, there are two units that we need to understand. One is CGS unit and the second is SI unit, right? And we will also see how the CGS unit is actually related to the SI unit as well. So in CGS unit, the heat is measured in calorie, and the symbol used for calorie is CAL. Okay. So how is 1 calorie defined as? 1 calorie is defined as the amount of heat required to raise the temperature of 1 gram of water through 1 degree Celsius. Okay. So raise the temperature of 1 gram of water through 1 degree Celsius. Okay. So I repeat, how is 1 calorie defined as? It is defined as the amount of heat required to raise the temperature of 1 gram of water through 1 degree Celsius, that is between 14 to 15 degree Celsius. Okay. So the reason why they took this 14 to 15 degrees Celsius is because few years back, they were assuming that this is the room temperature. So that is the reason why they gave this temperature. Okay. Now, what is going to be the SI unit of heat? So SI unit of heat, obviously, when you're saying heat is a form of energy, it is going to be measured in joule. And 1 calorie is equal to 4.186 joule, or we can also use 4.2 joule. Okay. So wherever we see calorie, you can replace it with 4.2 joule. And wherever you see joule, so 1 joule will be equal to 1 divided by 4.2 calorie. You can use this also. So the meaning of this is, if I take water exactly of 1 gram at 14 degrees Celsius, I need to supply an energy of 4.2 calorie, 1 calorie or 4.2 joule to raise the temperature of this water, which is at 14 degrees Celsius to 15 degrees Celsius. That is the meaning of this calorie. Is it clear?
Sir,
Tell me.
sir, that definition for 1 calorie is similar to the definition for specific heat capacity, right?
Yes, yes, it is similar.
Sir, is it the same or like?
It's similar. It is similar because here we say generally between 14 to 15 degrees Celsius. It's similar. Okay.
Okay, sir.
Yeah. See there, how we write there, what we do is, see, for example, yesterday I told no specific heat capacity, or other name for it is heat capacity. Sorry, other name for it is specific heat. So whether you call it as specific heat or specific heat capacity, they both mean the same. There, the value will be measured as 2 joule per Kelvin. So 4.2 is some random number, some x. Joule per kilogram per Kelvin. This meaning another means if I take 1 kilogram of a substance, I need to raise the temperature of that 1 kilogram substance through 1 Kelvin, then I need to supply this much amount of energy. But if I take only this x joule, right, this will become the unit of energy. So try to understand what I'm trying to say. If I write the same thing in terms of CJ's unit, then how will I write x calorie per gram per degree Celsius? Am I clear with this? Either one then another. When you see x calorie per gram per degree Celsius, this is what is called as specific heat capacity. Shri Kriti, are you able to understand this? But this x calorie, this is the amount of heat. So here I'm not talking about specific heat capacity. I'm talking only about 1 calorie. So 1 calorie means I'm concerned about this value. That's it. This and the numerator. If I take calorie per gram per degree Celsius, then I'm concerned about a parameter called as specific heat capacity. See, everything is related only. You will understand why they are related slowly. இது வரைக்கும் புரியுதாமா?
Yes, sir.
Okay. போலாமா அடுத்தது? So the next concept is Joule's mechanical equivalent of heat. Okay. So there is something called as Joule's law of equivalence between work and heat. See, for example, have you ever seen the backside of food items that they give you? They'll give you some specifications. No, sugar, this much percentage. Salt, this much percentage. Okay. Oil, this much percentage. That is cholesterol or whatever it is, this much percentage. You are able to understand what I'm saying. So beside that, they would have given you something in kilocalories. Did you ever observe that? Similarly, when you work out also, when you run, they'll ask you how many calories you burnt. They ask this question, no, for example, let's say you have burnt 500 calories. Actually, you have not burnt 500 calories, rather you have burnt 500 kilocalories. In general talk, we don't use the word kilo. So when you do a workout, you're able to generate equivalent amount of energy, which is getting burnt. So in a similar way, we can define the mechanical equivalent of heat. That is, we can define the mechanical equivalent of heat, which is called as the Joule's mechanical equivalent of heat. So from experiment, you can say that Joule established a relation between the work done and the amount of heat that is produced. So he told that whenever a given amount of work is converted into heat, always the same amount of heat is produced. So whatever is the work that you do, that work will get converted to equivalent amount of heat, not exact amount of heat. Means the amount of work done is directly proportional to the amount of heat that is getting generated. From this, I can say W is equal to J into Q, where J is called as the Joule's mechanical equivalent of heat. Suppose I want to find what is the value of J, then if I put Q is equal to 1 in this expression, okay, then I can say W is equal to J. So based on this, can you give a definition to it? So how is the Joule's mechanical equivalent of heat defined as? It is defined as the amount of work that must be done to produce unit quantity of heat. Why unit quantity of heat? Because we substituted Q is equal to 1. Okay, by substituting Q is equal to 1, we are able to say that the work done is exactly equal to the Joule's mechanical equivalent of heat. Now, what is going to be the SI unit of it? So SI unit of J is going to be Joule per, it is, okay. It's not the SI unit actually. Its value can be taken as, so value is basically 4.186 joule per calorie, right? When you write this in terms of erg, you can write 4.186 into 1 joule is 10 power 7 erg per calorie. And the most important point to be noted here is it is not a physical quantity, it is just a conversion factor. Because what did we say? When we do some work, an equivalent amount of heat is getting generated. So to find the conversion, what you need to do is you need to multiply the value of heat with 4.186 to calculate the amount of work that you have done. Okay. Now, so we saw what is heat, what is the unit of heat, then what is the Joule's mechanical equivalent of heat. Now we will concentrate on the term called as temperature. So basically, what is temperature? Temperature is the degree of hotness or coldness of an object, right? Suppose we have two objects which are placed in contact, right? Where will the heat flow from? Obviously, from a higher temperature object to a lower temperature object. So what are the other way in which you can define temperature? The temperature may be defined as the thermal state of a body, right? The thermal state of a body, which will decide the direction of flow of heat energy from one body to another. So what is the meaning of it? If there is an object, right? I have another object, right? I can say these two objects are at different thermal states in such a way. There is a parameter that will decide in which direction is the energy going to flow. Suppose the energy flows from here to here, then we can say that this object is the hotter object and this is going to be the colder object. That is the meaning. right? Right? Similarly, the temperature of an object is also the measure of average kinetic energy of its molecules. That is, when an object is heated, its molecules move faster, that is, their kinetic energy increases. So kinetic energy increases, thus the temperature of the object will also increase. Okay. So this is another way of interpreting it. So what I'm trying to say is, first of all, the simplest definition of temperature that is possible is temperature is a degree of hotness or coldness of an object. Means when two objects are kept in contact with each other, heat always flows from higher to a lower object. Heat always flows from an object of higher temperature to a lower temperature. Second is, temperature may also be defined as the thermal state of an object, which will decide the direction of flow of heat energy from one object to another. Right? Under what scenario? When they are placed in thermal contact with each other. Okay. So having said this, so we will try to understand the difference between heat and temperature. So heat is a form of energy which produces the sensation of hotness or coldness of an object, right? Whereas temperature is what? It is a degree of hotness or coldness of an object, right? So heat is a cause. So when heat is supplied to an object, its temperature increases, whereas temperature is an effect. So by you supplying the heat, you are actually changing the temperature of an object. Similarly, heat represents the kinetic energy of the molecules of the body, whereas temperature refers to the average kinetic energy possessed by the molecules of the body. Right? So next is, heat flows from higher temperature side to a lower temperature side, irrespective of the amount of heat possessed by the bodies in contact. So temperature, what does it do? This is the one which decides the direction of flow of heat from one body to another. Right? And lastly, heat is measured in calorie, kilocalorie, or joule, whereas temperature is measured in degree Celsius, degree Fahrenheit, or Kelvin. So this is the basic difference between these two parameters. Okay. Next is thermometry, right? So thermometry, thermo refers to,
Sir, what is the difference between total kinetic energy and average kinetic energy?
so heat energy we saw there, no? What did we see there? I wrote a mathematical expression, see. So energy of molecule is equal to kT, kV, and kr. So here I'm talking about the total energy of a molecule. Right? So it represents the total energy of molecules. Whereas average kinetic energy means you add all the values of each molecule and divide it with the total number of molecules that are present in it. So this is what is called as average. Average,
Sir, if we then divide it by n, then that is total kinetic energy.
That represents. Yeah, that is the total kinetic energy, and the total kinetic energy represents the heat that is present in the system. Whereas temperature speaks about the average kinetic energy of each molecule. I'm not sure if you have learned in kinetic theory of gases also, you have K is equal to 3, kinetic energy is equal to 3 by 2 into Kb into capital T. I'm not sure if you have seen this expression where Kb is called as the Boltzmann's constant. And this is called as the absolute temperature. And this represents the average kinetic energy possessed by the molecules. Means what I'm trying to say is each molecule will possess different value of kinetic energy. If you add all those values and divide it with n, that will give you what? That will actually not give you temperature. That speaks about temperature. Are you able to understand? So because I can never relate kinetic energy to temperature because those two are different physical quantities. But if I'm able to calculate the average kinetic energy of all the molecules that is present, that speaks or that gives us an information about the temperature of the system. If I add all the kinetic energy, that gives me information about the heat possessed by the system. That is what the difference is. Puriyadama?
Yes, sir.
Okay, next is thermometry. So what is thermometry? It is a branch of physics, right? Which deals with the measurement of temperature, right? So you can ask me then, what is the branch of physics that deals with the measurement of heat? Can you tell me?
Calorimetry.
Calorimetry. So thermometry refers to or deals with the branch of physics which deals with the measurement of temperature. And you know what is a thermometer? Thermometer is basically any device used to measure the temperature of an object, right? Right? It is named so because I don't want to get into those details. But what is the principle of a thermometer? But what is the principle on which it works? Because this will give us the relation between different scales of temperature. Okay, let us see what is the principle of a thermometer. So a thermometer makes use of some measurable property called thermometric property of a substance, which change linear with temperature. Right? The parameter that we are going to use will be directly proportional to the temperature in a linear form. Okay. So the thermometric properties of different substances and the corresponding thermometer are as follows. One is length of the liquid column in the capillary tube. So you would have seen a mercury thermometer, right? Has everyone seen a mercury thermometer, or you're used only to digital and thermal meters? Have you seen a mercury thermometer? Yes or no?
Yes, sir.
Yes.
In that you would have seen, right? There will be the mercury will actually rise with the temperature, right? So that mercury is actually placed inside a capillary tube. So this mercury thermometer works on the principle, or it takes a consideration of length of the liquid column in the capillary tube into consideration. Second is pressure of a gas at a constant volume. This is with respect to a thermodynamic parameter. Okay, there is something called as constant volume gas thermometer. Third is it depends on the volume of a gas at a constant pressure, which is called as a pressure gas thermometer, right? Then we have something called as a platinum resistance thermometer, which uses the concept of electrical resistance of a metal wire. Because we know this fact also, when current is passed through a material for longer duration, what will happen to it? It will generate heat of this value I square into R into T, right? So when heat is getting generated, obviously you can speak about the temperature, right? Similarly, we can talk about the radiated power also, which is for a pyrometer. So you will not be questioned about all these things. It's only for your knowledge. Okay. Now, this is important. So there are two fixed points on a temperature scale, right? So listen, whenever you want to construct a temperature scale, right, you need to have two fixed points, like how we have reference points. And those 2 points should have a well-defined thermodynamic states. Okay. So what are the states we will see? Okay. So the two arbitrary numbers are in such a way that one number fixes the origin of the scale. Origin in the sense, what is the lowermost temperature that is possible for that thermometer to measure. And the other fixes the size of the unit scale. So what the meaning of this is, observe. Here there are 3 different thermometers which are having different temperature scales, where one is a Celsius scale, the other is a Fahrenheit, and the other one is Kelvin. Okay. So if you see, when you take the bottommost point, that is the origin, for a Celsius scale, where is the origin starting with? It is starting with 0. right? Whereas for a Fahrenheit scale, it is not starting with 0, rather it is starting with 23. Then what about a Kelvin scale? It is 273. Okay. So see, now the question is, the temperature at which pure ice melts at standard pressure, that is ice liquid equilibrium state exists, is taken to be the lower fixed point. Okay. Similarly, the temperature at which pure water boils at atmospheric pressure is considered to be the upper fixed point. So are you able to understand this? So what will you take the lowermost point as? The melting point. And you will take the uppermost point to be the steam point. Okay. Now see. And what is the important point you need to have in mind? What is the principle I told you? The measurable property called as the thermometric property will change in what fashion? Will change linearly with temperature. Meaning, though the starting points are different, observe, though the starting points are different, one is 0, one is 32, and one is 273, the readings will be separated by equal number of distances. Means the number of divisions in all the scales is going to be the same. Or can I say, instead of saying the number of divisions are going to be the same, can I say that the distance between these 2 points will be a constant? Okay. Now, what I'm trying to tell here is, see, suppose I take some line here, and let's say at this line, the temperature in the Celsius scale is Tc. The temperature in the Fahrenheit scale is Tf, and the temperature in the Kelvin scale is Tk. Okay. Can I say in Celsius scale, 100 minus 0, 100 minus 0 divided by Tc minus 0 will be equal to 212 minus 32. 1 minute. 212 minus 32 divided by, tell me what should come in the denominator? Tf minus 32, right? So when I take this value and calculate, I'll get 100 divided by Tc is equal to 212 minus 32 is going to give me 180 divided by Tf minus 32. So basically it is like I'm writing the slope of that line. Okay. So here it is going to be 5 times and here it is going to be 9 times. When I divide it with 20, then Tc divided by 5, if I take the reciprocal of it, will be equal to Tf minus 32 divided by 9. What is the meaning of this? You've seen this mathematical expression. Suppose I give you the temperature to be 50 degrees Celsius. If I ask you to convert it to Tf, how will you write it? Then you use this expression. Then how will you do the conversion? 50 divided by 5 is equal to Tf minus 32 divided by Tf minus 32, the whole divided by 9. So this goes 10 times. So Tf minus 32 will be 90 and Tf will be equal to 122 degree Fahrenheit. Means on a Celsius scale, if you have 50 degrees Celsius, In a Fahrenheit scale, you will have it on 122 degree Fahrenheit. If you want to make a note of something, make it. And if there is any doubt, get it clarified. Okay. Similarly, if you want to do the conversion from Celsius to Kelvin, what will you do? Or how will you do? Tk minus 273 divided by 373 minus 273 will be equal to Tc minus 0 divided by 100 minus 0. Right? Just give me a minute. Okay. So what were we discussing? Yeah. Tk minus 273 divided by, so Tk minus 273 divided by 100 will be equal to Tc divided by 100. This and this will get cancelled. So Tk will be equal to Tc plus 273. You remember? So whenever the temperature is given in degrees Celsius, what will you do? You will add a 273 to it. Why do you add it? Did you understand now? Yeah. Clear with this, guys? Next. So this part and all, we will not waste time. Okay. So now write down the heading as thermal expansion of solids. Okay. So basically, when you take a solid, right, and when the solid is supplied with some heat, So its temperature is obviously going to rise, no doubt in that. But at the same time, you can also observe that the dimensions of the object will also change. So how are they going to get changed is what we will see now. Okay. So when I talk about the thermal expansion of solids, there are three kinds of expansion we can speak about. One is called as linear expansion, right? The second is called as surface expansion, and the third is called as volume expansion. Okay. Now, what is linear expansion? So observe, if I take the initial length of the conductor to be L naught, right? And initial temperature, let me call it as T. When the temperature is changed from T to T plus delta T, then you can observe that there is a change in length that is going to take place. Okay. So that delta L is basically final length minus initial length. Okay. And what is observed is delta L. The charge in my pencil is getting over. So delta L is observed to be directly proportional to the initial length. Okay. Similarly, delta L is observed to be directly proportional to the change in temperature. Directly proportional to the change in temperature. So delta L is directly proportional to L naught into delta T. Then this delta L, see proportionality symbol, I'm using it slightly curved like this. Okay. Then delta L, when you remove the proportionality symbol, is observed to be equal to alpha into L naught into delta T. Okay. So delta L is equal to alpha into L naught into delta T, which implies delta L will be, okay, delta L is basically what? L final minus L naught is equal to alpha into L naught into delta T, which implies L final will be equal to L naught into 1 plus alpha into delta T. So this is going to be the final length of the conductor. L naught into 1 plus alpha into delta T, where this alpha is called as the temperature coefficient of linear expansion. So it's called as the temperature coefficient of linear expansion. Okay. Now, how can I write this alpha as? If I rearrange, so since L final is equal to L naught plus L naught into alpha delta T, what can I write this value of alpha as? It is L final minus L naught divided by L naught into delta T. So alpha can be written as change in length divided by original length into change in temperature. So change in length divided by original length into change in temperature. Okay. So what is going to be the SI unit for it? SI unit will be Kelvin inverse and CGS unit will be degree Celsius inverse. Is it clear till this step?
Sir.
Tell me that. You called me or you told clear?
Yes, sir.
Oh, clear.
Yes.
Okay. Similarly, the next one is surface expansion. Suppose I have a two-dimensional object in my hand, which is a planar object basically. When temperature is supplied to it and let's say its dimensions is changing in such a way that there is a change in area that is taking place. If I take the initial area to be A naught and the final area to be A final, then delta A is given as A final minus A naught. So have this in your mind. So the same logic again, delta A is observed to be directly proportional to the change in temperature. Okay. Similarly, delta A is observed to be directly proportional to the initial area itself. Then when you combine these two, then we can write delta A is directly proportional to A naught into delta T, or delta A will be equal to beta times A naught into delta T. So what is the value of delta A? It is A final minus A naught, which is equal to beta into A naught into delta T. So what is going to be the value of A final? A final will be equal to A naught into 1 plus beta into delta T, right? So this is going to be the final area of the object, and this beta is called as coefficient of superficial expansion. Okay. So again, if you write the value of beta from here, you can write beta is equal to delta A, or I can write it as A final minus A naught divided by A naught into delta T. So this is going to be change in area divided by original area into change in temperature. Okay. Okay. So again, the value of beta is also going to be in terms of beta will also be in terms of degree Celsius or Kelvin inverse. So beta is also measured in degree Celsius inverse or Kelvin inverse. Okay. So surface expansion, areal expansion, or superficial expansion, everything means the same. And the last type of expansion we will see is volume expansion. So volume expansion is again when you have an object which has a volume associated with it. Okay. So let's say the initial volume is V naught, and when temperature is supplied, its volume becomes V naught plus delta V, where delta V naught plus delta V is going to be V final. Okay. Then what we can write is the change in volume is observed to be directly proportional to the initial volume. And change in volume is observed to be directly proportional to the change in temperature. So which implies delta V will be equal to gamma times V naught into delta T. And delta V can be written as V final minus V naught is equal to gamma into V naught into delta T, which implies V final will be equal to V naught plus 1 into V naught into 1 plus gamma into delta T. And this gamma is called as the coefficient of volume expansion. So again, gamma will be equal to delta V divided by V naught into delta T. So this is also measured in degree Celsius inverse or Kelvin inverse. So these are the three main types of expansions that have taken place in solids, right? Where alpha is called as the coefficient of linear expansion, right? So here coefficient means I'm calling it as temperature coefficient. So then beta is called as the temperature coefficient of superficial expansion, and gamma is called as the temperature coefficient of volume expansion. Okay, having said this, now we will see relation between alpha, beta, and gamma. Okay, so now we'll see the relation between alpha, beta, and gamma. So how to do that? Observe. Suppose I consider a cube. Suppose I consider a cube of side L. Okay. So when you supply temperature to this object, what will happen is length will change, area will change, volume will also change, right, in such a way that L final will be equal to L naught into 1 plus alpha into delta T. So let me call this as equation number 1. So what is L naught? It is L. Now area final will be equal to, okay, let me write it in a different way. So L final will be equal to L naught into 1 plus alpha into delta T. So L final, can I write it as L into 1 plus alpha into delta T, which I'll call it as equation number 1. Similarly, A final will be equal to A naught into 1 plus beta into delta T. So what will be the value of A final? A final will be equal to A into 1 plus beta into delta T. So, but what is A? A is L square. So L square into 1 plus beta into delta T. Can I write it like that? Okay, I'll do one thing. So A final is actually L final square. So can I write L final square is equal to L naught square into 1 plus beta into delta T. Right. So this will be equal to L square into 1 plus beta into delta T. Now let me call this as 2. Using 1 in 2, in the sense, in the place of L final, I'm going to replace with this. Observe. So how I'm going to replace this? In the place of L final, I will write L into 1 plus alpha into delta T. So L into 1 plus alpha into delta T, the whole square, will be equal to L square into 1 plus beta into delta T. Okay. Now, this will be L square into 1 plus alpha square delta T square plus 2 times alpha into delta T. This will be equal to L square into 1 plus beta into delta T. So here L square and L square will get cancelled. From this I can conclude that 1 plus alpha square into delta T the whole square plus 2 alpha delta T is equal to 1 plus beta into delta T. So 1 and 1 are lost. And remember, alpha is very small such that alpha square can be approximated to 0, meaning I can take this value and put it here, which will become a 0. So what are we left out with? We are left out with 2 times alpha into delta T is equal to beta into delta T. So delta T and delta T are gone, which implies beta will be equal to 2 times alpha. Okay, beta will be equal to 2 times alpha. Make a note. So let me know once you're done copying. Okay. Similarly, we know that L final is equal to L into 1 plus alpha into delta t. Similarly, what can I write V final as? V final will be V naught into 1 plus gamma into delta t. But what is V naught? V naught is L cube into 1 plus gamma into delta t. Right? So let this be 3. So using, okay, 1 minute. I'll not call this as 3. I'll write another step. So volume final, can I write it as L final cube is equal to L cube into 1 plus gamma into delta t. This is 3. So what I will do is, using 1 in 3, what will we get? You will get L into 1 plus alpha into delta t, the whole cube, is equal to L cube into 1 plus gamma into delta t. Right? So when you expand and write it, you will have L cube into 1 plus alpha delta t, the whole cube, is equal to L cube into 1 plus gamma into delta t. So what is A plus B, the whole cube? It is A cube plus B cube plus 3A square B plus 3A B square. This is the left hand side. This will be equal to L cube into 1 plus gamma into delta t. So L cube and L cube are lost. Again, alpha into delta t, the whole cube, is approximated to 0. This is approximated to 0. So which implies 1 plus 3 alpha delta t will be equal to 1 plus gamma delta t. So 1 and 1 will get cancelled. Delta t and delta t are gone, which implies 3 alpha is equal to gamma. So we are clear that alpha is to beta is to gamma will be equal to alpha is to, what did we get the value of beta as? So we got beta is equal to 2 alpha. So alpha is 2, 2 alpha is 2. Gamma, we got it as 3 alpha is equal to 1 is to 2 is to 3. So alpha is to beta is to gamma will be equal to 1 is to 2 is to 3. So this is another important expression to be remembered. Yeah. So make a note. Let me know once you're done. Okay. So this is all about the first part of this chapter. Okay. We have two more parts, that is calorimetry. And the last part is about the heat transfer. Okay. So I'll just give you an introduction to calorimetry and then we'll wind up the session. So as I told you in the beginning, calorie is heat, metry is measurement. So if we talk about a branch of physics which deals with the measurement of heat, then we call that branch as calorimetry. And the second point that we are supposed to know is the principle of calorimetry. The principle of calorimetry states that when two objects are placed in contact, right, then the heat exchange will take place in such a way that the heat lost by the hotter object will be equal to the heat gained by the colder object under isolated conditions. Okay. So the meaning is, if I have an object at temperature T1 and T2 and they both are brought in contact with each other, if suppose I take T1 to be greater than T2, then heat lost by first object will be equal to the heat gained by the second object, again under isolated condition, and this is called as the principle of calorimetry. Okay. Is it clear? Yes or no? Yes, I'm talking to you. Is it clear or not?
Yes, sir.
Okay. So with this, we'll wind up. Next class, I'll discuss about the heat transfer and some more problems.
Thank you, sir.
Indeed.
Sir.